Can you hear me? Those of you who have already joined, can you hear me? Okay. So we'll start at exactly 7. Wait for others to join till then. And meanwhile, I'll just discuss what I'm going to review today. So today will be the calculus review. And in this, I plan to cover some special functions, rather special types of functions. Yes, good evening. And of course, limits of functions not really concerned with sequences. Continuity, I plan to cover differentiability, obviously. And some rules in differentiability and applications, things like increasing, decreasing functions, and so on. Else, mean value theorems, they should be a part of differentiability, I'm sure. Mean value theorems, integration, and applications. The Leibniz rule. And that's it. That's what we plan to cover today. And if, okay, let's see. So it's 1 more minute and we'll start at exactly 7 in my clock. And let us begin. So we will start with functions then. Okay. So the basic definition of a function, in case you may have forgotten it or are rusty. So a function from x to y, so x and y are sets, is a rule. So in very simple terms, is a rule that assigns to each value in x on one and only one element of y. Okay, x is called the domain of the function, y is called the codomain, and then you have something called the range, which is set of all possible outputs, or rather all outputs that actually occur. You want it more precisely, this is the set of all y in y such that there exists some x in x such that fx is y. This is the precise definition of the range. But let's not talk too much about this. I'm sure all of you know. Even function. So a function is said to be even if fx is equal to f of minus x for all x belonging to x. So unless I start mentioning something else, x will be my domain, y will be my codomain. And a function is said to be odd if fx is equal to minus of f minus x for all x belonging to x. Okay. Then a function is said to be periodic if there is some p that's positive and real, of course, such that f of x plus p is equal to f of x for all x belonging to x. And the smallest such p is called the period of f. So there's that. And some properties of the period that I guess you should know. There might be an objective problem based on these. So if fx is periodic with period p, so p obviously belongs to this set, then I have the following. For any real a and any real b, so a and b are real constants, then that this function afx plus b also has period p. And secondly, f of ax plus b has period p over mod a. Okay, that's that. Fine, then you have functions that are injective, surjective, and bijective. Once again, something I hope that all of you already know. But let's state it anyhow. F is injective if fx1 is equal to fx2 implies that x1 is equal to x2. Or equivalently, x1 not equal to x2 implies that fx1 not equal to fx2. There's that as well. But this is good enough. Then f is surjective. For this definition, let me write it this way. F from x to y is surjective if y is equal to range of f. F is bijective if it is both. Fine. What now? Okay, what's so special about bijective functions? So a bijective function lets me define an inverse, which I like. Okay. So if f from x to y is bijective, then I can go the other way around. Then there exists a unique function, say, or rather let's just call it f inverse. So this is not 1 over f, this is just a symbol. It's not the reciprocal from y to x, such that f inverse y being equal to x is the same as saying f of x is y. So of course then this implies that f inverse fx is x, and this is the same as f of f inverse x. So that's x. That is, if f inverse is the inverse of f, then f is the inverse of f inverse. So that is, f and f inverse are inverses of each other. Okay, so far so good. So far everyone knows everything. Great. Now let's come to limits. So we can put a tick mark on this, I guess. This is done. Now let's come to limits. So you know what the limit is, right? You know how it is defined, of course. You've seen those. So I don't want to bother writing the whole left hand, right hand thing right now. So let's just go to the properties that you don't realize. Let's look at some immediate properties first, I suppose. So for this board, on this entire board, assume that limit x tends to a of some fx is L1, and limit x tends to a of some gx is L2, where L1 and L2 are finite. So where L1 and L2 belong to R, it's one way of saying they're finite. Then you have first limit x tends to a c1 fx plus and minus c2 gx is equal to c1 L1 plus c2 L2 for all c1, c2 given constants, given real constants. Then you have the product, which works as you would expect it to. So limit x tends to a fx gx is equal to L1 L2. Great. Then you have limit x tends to a fx over gx is equal to L1 over L2 if, or rather provided, L2 is non-zero. Otherwise you can't define this, of course. Not immediately anyhow. There will be some cases where you'll be able to define it still. And the one that maybe you haven't seen before is that limit x tends to a of the composite, so of f of g of x is equal to f of limit x tends to a g of x, which is equal to f of L2. So this only happens, so you can say this only when, so if and only if fx is continuous at x is equal to L2. So only if it is continuous can you say this. Otherwise this will not hold, not always. Okay. Now some standard limits. So these are the limits that you should have memorized, that are handy to know immediately. Nine. So first, limit x tends to 0 sine x over x is equal to limit x tends to 0 tangent of x over x, and this limit is equal to 1. So here x is in radians. Not that it really matters, because if it's going to 0 in radians, it's going to go to 0 in degrees as well. But still, doesn't hurt to define one convention we're going to follow. Then you have limit x tends to 0 of the arc sine function. Do all of you know what arc sine stands for? For anyone who doesn't know? 10 people in class. Is there someone who doesn't know what arc sine is? I'll just type yes or no. If you know, that's fine. If you don't, type no. Yes, it's just sine inverse. Yeah. Arc sine is just sine inverse. I write arc sine to avoid ambiguity. And yeah. So arc sine x over x is equal to limit x tends to 0 arc tan x over x, and this is also 1. Then you have limit x tends to 0 e to the power x minus 1 over x. This is 1. E is of course the base of the natural log, and a more generalized form of this, so I'll write next to it, would be for any a. You have, so whenever you can define this anyhow, non-zero a, e to the power x minus 1 over x. This limit is log of a to the base b. So then a here belongs to positive reals. Okay, perfect. Then you have this limit of x tends to 0 log e. So is it fine if I write ln instead of log to the base e every time? So ln stands for the natural log. This limit is 1. And once again, slightly more generally, you have limit x tends to 0 log to the base a 1 plus x over x is log of e to the base a. So of course, then the condition over a is that it is positive and not equal to 1. You can avoid memorizing number 4 and number 6 because they can be easily converted into a case of number 3 and number 5 respectively. Okay. Then you have these limit x tends to 0 1 plus x to the power n minus 1 over x. This limit is just n, right? Then you have limit x tends to 0, 1 plus x, 1 over x is equal to e. And a similar looking limit is when limit x tends to infinity instead, and you replace this with this and this with this. So this is of course also e, because as x goes to infinity, 1 over x goes to 0. And this is just the same limit written in two different forms. Fine. And finally, one more limit that doesn't hurt to know is limit x tends to some a, and you have x to the power m minus a to the power n over x to the power n minus a to the power n. This limit is equal to m over n a to the power of m minus n. Fine. So these are the limits that you should memorize. And then we have an important result while evaluating limits. So the sandwich theorem, which states that let f, g, and h. I have three functions, fx, gx, and hx, be three real functions. With common domain. So that's necessary, otherwise you don't really get to define what I'm going to define. With common domain. So note that the entire domain doesn't need to be the same. Even if it's just some small neighborhood around the point of which I'm going to talk about, that's also good enough. Because we are only concerned with the limiting tendency, not the entire function itself. So such that f is trapped between h and g for the entire domain. Once again, this domain could be something as small as a neighborhood around my point A, which we'll soon see. It doesn't have to be what you, the every possible value where this function is defined. Then, so the then leads to another condition. If the limits of h and g are same, some point A. Note that A could also be infinity, so saying a point is not really correct. So limit x tends to A, hx is equal to limit x tends to A, gx, say this is some L, then the limit of fx as x tends to A is also L. Fine. Is there anyone who hasn't seen this before? Nope. Okay. Now, a few more special types of limits, or rather how you evaluate them. So important forms of limits. So the first one is a limit of the form limit as x tends to a of some function fx raised to another function gx. How do you evaluate this? There are two cases which are which don't really have much difference between them, but let's still mention them anyhow. So case one is when this fx goes to 1. In this case, you realize that limit x tends to a fx gx is equal to limit x tends to a 1 plus fx minus 1 to the power of gx. So this I can then write as this quantity 1 plus fx minus 1 over x minus 1. Note that this goes to 0, this power, so this goes to 1 over 0, which is absurd. Gx times fx minus 1 over like this, like this, like this. So here my power is gx times fx minus 1. Okay. And then you can magically realize, so I'm not going to justify this too much, but this is equal to this thing. I don't know the whys and the hows. Not going to go into those. You can fill in the blanks here if you would like to. Then you have case 2. Case 2 is when limit x tends to a, fx is not equal to 1, but fx is still positive in a neighborhood of a. Or some neighborhood of a. By neighborhood, I just mean some interval a minus delta a plus delta, where delta can be as small as you'd like. In this case, you write that fx gx is straightforward equal to the power gx log base c ln fx. And then, of course, the limits follow. Okay, done. Then there is another special type of limit that we are repeatedly concerned with, and this is the limit of the type limit x tends to infinity e to the power x, where a is some given constant, so you know what a is. A doesn't really vary for my cases. So case 1 is when a is some fixed value between 0 and 1. Then the limit is of course 0. Case 2 is when a is equal to 1, in which case I'm sure all of you will agree the limit is also 1. Case 3 is when a is larger than 1 and a greater than 1. Then you have that this, so this is not a, sorry, this is infinity. Limit x tends to infinity, then goes to infinity as well. Okay. So that covers limits. That's all you need to know about limits. Perfect. Any doubts so far? None? Okay, then we move on to continuity. So a function is said to be continuous. A function, So my definitions are not very precise. So I'm omitting things like what is the domain, what is the codomain, and blah blah blah, because you all should know how to define these beforehand regardless. So a function is continuous at some x is equal to a if two conditions hold. First, you need the limit to exist, and then you need the limit to be equal to the value at that point, value of the function at that point. Okay. Then, of course, some very elementary facts. So if f and g are continuous at some point a, at some point x is equal to a, then you can multiply with some constant, and that is also continuous at a. So see some fixed constant here. Their sum and difference is continuous at that same point. So is equal to a. Their product is also continuous. That point. And then finally, this thing, fx over gx, is continuous provided gx not equal to ga not equal to 0. Okay. And then, of course, a function is continuous in some interval, some open interval, if it is continuous at every point in the interval. And there's really no notion of continuity over closed intervals. If you really want to force one, you could take the left hand and right hand limits at the end point and only care about those. But it's not a notion that's very useful. So that covers continuity. Now we come to differentiability. Differentiability. Okay. So once again, you should all know when a function is said to be differentiable. So a function f fx is said to be differentiable at x is equal to a if it is firstly continuous. So okay, never mind. Let's not worry about that. Continuous at x is equal to a. And secondly, this quantity, this limit, exists. So all you need is its existence and is finite as well. And is finite. Then you say that the derivative of f with respect to, so a function y is equal to fx rather, then the derivative of fx with respect to x can be written as dy over dx, and this is equal to this limit. Okay. Then let me write down some standard derivatives that you should have memorized. Some standard derivatives. So d over dx x to the power n is an xn minus 1. The derivative of any constant is 0. An interesting fact, maybe not so much at first glance, is that the derivative of e to the power x is the same as the function itself. So you can keep differentiating this as much as you like, you won't get another function out of it. D over dx of, okay, let me take log here, of log to the base e is 1 over x. So here you assume that x greater than 0, of course, otherwise my log isn't really defined. Then you have d over dx sine x, this is cosine of x, d over dx of cosine of x is negative of the sine of x. Great. D over dx over tan x is secant squared x. D over dx is the cotangent of x is negative times the cosecant squared of x. Derivative of the cosecant function is negative cosecant of x times cotangent of x. Similarly, the derivative of the secant function is secant of x times the tangent of x. And if you want to remember which ones have a negative, those that start with a c have a negative. Fine. Okay. Then you can differentiate the arc functions as well. So the inverse trigonometric functions. So d over dx of arc sine x is just 1 over root 1 minus x square. D over dx of the arc cos function, arc cos x is negative 1 root 1 minus x squared. The tangent function, or rather the arc tangent function, is a derivative you will see repeatedly. Arc cot squared. And maybe not such frequent visitors while solving problems, but still something you should know. Arc of cosec x is minus 1 mod x root over x squared minus 1. And arc secant is 1 over mod x root x squared minus. So once again, you only get the negative when this thing starts with a c. Okay. So these are the standard derivatives that you should memorize. Maybe there will be some more further, we'll see. Okay. Then similar to limits and similar to continuity, you can do things with differentiable functions and easily find the limit. So for two differentiable functions, differentiable at some point, of course, but of course the context should be clear to you without me writing too much. Say fx and gx, I can take the derivative of their sum, or rather any linear combination. So a and b are some given constants. Then the derivative simply splits over the sum. Nothing fancy. Then if you have a product, then you have what's called the product rule. So this is where it stops being too obvious, but still I'm sure all of you know this. Then this is derivative of one times the other plus derivative of the other times the first one. Okay. Similarly, when you have division, then also it's not very trivial. Then this is f dash x gx minus fx gx dash g dash x rather divided by g of x squared. Okay. And then you have what's called the chain rule. So if you have a composite function that you're trying to differentiate, then you get something like this. Okay. Now there's something, so a disclaimer first. Only use the following in objective problems. Do not use this in a subjective problem. Or MCQ problems. So anywhere your solution doesn't need to be worried about only the answer in the end. So in MCQ problems only. And most of you may know this. So this is called L'Hopital's rule. And without really caring too much of why or how, this is what it states. Let fx and gx be differentiable if limit x tends to a fx is equal to 0 and so is no, I don't think anyone is saying anything for whatever reason. Or were you typing something before? Because I didn't get any messages. And this is the same as this. Then or equivalently, or both of them are infinite. So both of these are infinite limits. Then the limit x tends to a fx over gx is the same as the limit of both of these differentiated. Okay, perfect. Now some random facts, some random geometric facts rather. Dy over dx represents the rate of change. So in words, you could also say that this is the rate of change of y with respect to x. So how much does y change when you change x? It also represents the slope of the tangent to y is equal to fx at the point x comma y. Okay. A more interesting fact, the angle between two curves, say fx and gx. So I just say curve, it doesn't need to be a conic or something special like that. Any old curve will do. So first of all, how do you describe the angle between two curves? So it is the angle between their tangents at their intersection. So if they don't intersect, you don't define this. Or you describe some arbitrary convention, you call it zero, for example. But I don't think that's very helpful because there might be common tangents. So yeah, so maybe you just don't define it at their intersection and is given by, this is the interesting part. So if it is phi, this angle, then tangent of phi tan function is equal to f dash alpha comma beta. So alpha beta is the intersection. I write f dash alpha comma beta in case your y is equal to fx can't really be brought down to a form of y is equal to fx. If you can find dy over dx in terms of both y and x, that's also good enough for this purpose. So here alpha beta is the intersection and phi is the angle. Okay. So you've seen a similar formula before. Angle between two lines, for example, is slope of first minus slope of second over 1 plus the product of its slopes. And similar to that situation here also, you immediately realize that two curves are orthogonal. So that is their angle, the angle between them is 90 degree. If f dash alpha beta times g dash alpha beta is minus 1, then they are said to cut orthogonally. Okay. So these were some random geometric facts. Now you try to investigate the nature of a function, which is a big deal. So increasing and decreasing functions. Let fx be a function that is continuous and differentiable on a comma b. So maybe continuous or it's finite. Maybe I should write it. So let's say continuous on a closed interval to have a stronger condition for us. So on closed interval AB and differentiable on open interval AB. So there is no notion of differentiability on closed intervals. You can get away with continuity using one-sided limits, but there is no idea of differentiability for the closed interval. On A comma B, then fx is strictly increasing. If the derivative, so let me put this strictly in a bracket and then mention the strictly condition in a bracket here. So that way I don't have to write this 4 times. It's strictly increasing. So for strictly, the equality is removed. And similarly, fx is decreasing if the derivative is non-positive and strictly decreasing if it is always negative. Okay. So a function that behaves similarly on an entire interval is said to be monotone on that interval. So fx is called monotonic in the closed interval a comma b. So to describe on the closed interval, of course, you check the endpoints immediately after you check the rest using the derivative. You don't get away with the intervals if you don't, on the closed interval if you don't check the endpoints individually. So if it is either entirely increasing or decreasing, either always increasing or always decreasing, on a comma b. Okay. And then I define something called maximas and minimas. Okay, so test for extrema. So before I go there, I describe or I define the points for which the derivative is zero or simply not defined are called the critical points. Yes. Okay. Then you have two ways of testing for local maxima and local minima. The first one is the first derivative test. This is the more powerful test compared to the other one because you only need the first derivative to exist. But of course, this one is also slightly difficult to use in some circumstances because this depends on the idea of a neighborhood. You need a small enough neighborhood, and it's not always easy to decide if there is some such small enough neighborhood or not. Okay, so let fx be continuous in some interval c minus h, c plus h. So some neighborhood of c. Then case 1, if x is equal to c is a critical point, and f dash x changes from positive to negative. So it increases while coming towards C and then immediately starts decreasing upon moving left to right. Can someone confirm if I'm audible once again? I had a connection failure. Okay. So where was I? So if x is equal to c is a critical point and f dash x changes sign from positive to negative upon moving left to right through C. Through C, then x is equal to c is a local maximum. Notice the word local, just being able to say this is not good enough to say that this always happens. Okay, so that this is the largest value the function can take. For example, you may have something that looks like this, in which case this test will say that this is a maxima, this is a maxima, this is a maxima, and you'll have to compare those three to check. And even worse, you might have something like this, which then goes here, and maybe something that jumps all the way here, in which case you won't even find these points by this test because it won't be continuous. So investigate your function properly before deciding on a global maxima or a minima. Okay, so similarly, if x is equal to c is a local, or rather, no, sorry, is a critical point, not a point. It's a critical point. Critical point, and so this time f dash x changes signs, but the other way around. So fx changes from negative to positive. upon moving left to right to C, left to right through C, then C is a local minima. But what happens if it doesn't change sign? That's entirely possible. So if it doesn't change sign, then you call it a point of inflection. So if f dash x doesn't change sign around C, then you call x is equal to C a point of inflection. You don't need to worry about what it is, just know the name and draw the graph to see what it looks like. Okay. This is the test I don't think any of you really use. What you do is work with second derivatives. So let fx be a function such that f dash x, so the first derivative, and f double dash x, and that is the second derivative, exist, and fx is continuous in some interval, some neighborhood of C, and fx is continuous on C minus h, C plus h. Then you say that x is equal to C is local maxima if f double dash x is negative, x is equal to C is local minima if f double dash x is positive, and this test is inconclusive if the second derivative is 0. So note that the second derivative, the sign of the second derivative only tells me if the first derivative is increasing or decreasing. So when I say that f double dash x is less than 0, what that means is that f dash x is a decreasing function. And I know that it is 0 at C. So it must have been positive to the left of C, and as soon as I crossed over to the right, it becomes negative, similar to the previous test. Okay, and a similar argument works for the local minima. Minima case. Okay, now mean value theorems. So you need to know 2 of these. I'll tell you 3 of these. If you don't know the third one already, you don't need to worry about it. First one is Rolle's theorem. This one states that if fx is continuous, in this interval, closed interval, and differentiable in the open interval, such that there is a special condition fa is equal to fb, then there is some c. There will be more than one, but you are sure that there is at least one. So there is at least one c in this open interval such that the derivative is 0. Graphically, this tells me, so if I have A here and B here, this is FA, this is FB, then what this tells me is that there is at least some tangent to this curve which is parallel to the x-axis. But I don't think you really need like it's ever useful. I have never used it in a graphical sense. So maybe just focus on the calculus for now. It's not worry too much about the graphs. Okay, this is Rolle's theorem. Then you have the mean value theorem, the one that you already know, all of you should know, which I'll call Lagrange's mean value theorem, so MVT for short. And this one removes the condition of FA being equal to FD from Rolle's theorem. So this states that if Fx is continuous on A comma B and differentiable on the similar open interval and differentiable on this thing, then there is at least one. So then there is at least one C in this open interval such that f dash C is equal to FB minus FA over B minus A. So you can immediately see that if FB is equal to FA like it was in Rolle's theorem, then this boils down to the same thing. Okay. Then you have one more, which if you don't already know, you should not worry about now, which is Cauchy's or Cauchy's mean value theorem, whichever pronunciation you prefer. And this one is slightly different. So this one doesn't really take anything away from Lagrange's mean value theorem. Doesn't really get rid of any conditions, but it still gives me something else. So it's something similar, but not quite a generalization. You can still get LMVT out of this, of course, but it's not immediately obvious as it was with Rolle's theorem and LMVT. So continuous on the closed interval and differentiable. So immediately one difference is obvious. This time I'm playing with two functions instead of just one. So if it is differentiable, the open interval, such that the derivative of g is not 0 for all x in A comma B, then there exists some C belonging to A comma B. So at least one you are ensured, such that f dash C over G dash C is FB minus FA GB minus GA. Okay. So to get LMVT out of this, you need to set gx to be the identity function. So you set gx is equal to x for all x, and you get Lagrange's mean value theorem out of it, right? So done. Everyone follows three of these. In that case, I will move on to integration next. Let's go back to board one. So tick mark on these two. So integration and Leibniz will be left. I won't define integration, so you just accept that there is something called integration. And there is one common misconception, which is that the derivative of a function can always be integrated. That is not correct. That is not correct. Do you know the expansions? You don't need to know the general Taylor expansion. Do you know the special expansions? So do you know the expansion of things like sin x, e to the power x, and all of those things? Yes, so expansions of standard things. So e to the power x, sine x, cos x, some log functions as well. Let me see if I have those in my notes. Maybe I'll mention those. Give me a minute. Okay, so this seems like a good point. So let me just find uh, one. So I'll write the ones that you need to know. And they are these. Yes. So Taylor expansions to know. Thank you for reminding me. I did not remember to discuss this. First one is the expansion of e to the power x, which is 1 plus x square over 2 factorial plus x cube over 3 factorial and so on. So for consistency's sake, I guess you could write this as like so and so on. Yes, sometimes there is an objective on this. So you'll be given some weird looking infinite summations and you have to evaluate them. So there are some in Tomato, in fact. But just the ones that I'm mentioning are all you need to know. You don't need to know the general thing. So this one is an alternating summation over the odd. Yeah, don't worry about the Maclaurin series. No, no need to worry. No, no. Cos x varies over the, or rather jumps over the even powers. Alternates over the even powers. Fine. Then you need to know these two as well. The natural log of 1 plus x is x minus x square over 2 plus x cube over 3. So no factorial here, just plain numbers. And the condition that you need to make sure that is holding here is that mod x is less than 1. And these are the four that you need to know. That's all. Okay. So let's move to integration now. So I'm not going to waste time defining what integration is and so forth. And instead, I'm just going to write some integrals straight away. So the ones that you need to know, integral of just dx, you call this x plus c. So c is the integration constant. Assume it is there if I forget to write it somewhere. The thing is that this thing, so indefinite integration is not really a thing. When you actually define integration, you only do it for definite integration. Indefinite integration is just something that we use as a trick of sorts to remember things. And we like to interpret it in various ways or whatever, but it's honestly it's meaningless. So in this one, a needs to be positive. Okay. Uh, some trigonometric integrations as well. Is minus cos. Cos is just sine. For tan x, you have natural log secant. For cot x dx, you have natural log of sin x. For cosecant x dx, you have natural log of cot x minus cosec x. C for secant of x dx, you have natural log sec x plus tan x plus c. Oh yeah. So these two can also be written as, so this one is the same as tan x over 2 c. This one is tan x over 2 plus pi over 4 plus c. Okay. And then few more standard ones. Cosec x cot x dx is equal to minus cosec x plus c sec x tan x. Okay. So these all of you know, like I'm just quickly writing them, so in case someone who hasn't seen these can fetch the boards and see them later. Okay. Then you use integration to calculate area. And okay, no, let's come to those later. A few more before I go there. This is Vx. This one is arc sine x over a plus c. One second. Okay. Yeah. So this, then dx over x square plus a square is equal to 1 over a tan inverse arc tan x over a plus c. And you don't need to. Okay. So a special form is this thing which is often very useful. So if f is some differentiable function and you have to integrate this thing, then this is just straight away e to the power x of x plus c, of course. Okay. Then integration also satisfies some properties, some neat properties. You can multiply constants and take them out of the integration. You can add and subtract. Blah, let's not worry about those now. Something to worry about is what's called integration by parts. So the integration of fx gx dx is fx times integration of gx x minus the integration over the derivative of fx times the integral of gx dx, and then a dx outside here. So you need to be smart about choosing your fx and gx, of course. And this is the formula. So this is called integration by parts. Surely all of you know this. Okay. Let's take a look at some standard substitutions. So form and the substitution you usually make. Okay. So if you have something of the form x square plus a square or square root over x square plus a square, you substitute a is equal to a tan theta or x is equal to a cot theta, whichever is convenient in that particular situation. Then if you have something of the form x square minus a square, my bad, minus a square minus a square, so this is in this situation you substitute the secant instead, secant and cosecant. Okay, if you have this in the other way around, square root over it, then you put sine theta and cos theta instead. So these are three standard substitutions that you need to know. I guess there is one more that you should know. So if both root a plus x and root a minus x are present or are involved, in that case you try to substitute a cos 2 theta. Of course, none of these are guaranteed to work, but they are what you should try first. Okay. Now, as I was previously saying, as all of you already know, you use integration to find the area. So there are some more standard formulae that you should remember. X square plus a square dx. This is the natural log of this thing. For x square minus a square, you flip the sign inside the square root only. If you get rid of the square root in this denominator, then you get this. Okay. Now, if you have something like a circle, maybe not a circle, but something of this form, then you get this long formula. Plus the constant. Similarly, if it is a negative in the square root, then this time the sign changes in two places, or three rather. So firstly it changes inside the square root, then it changes outside here, and then again in the square root inside. Okay. Arc sign. Okay. So these are the standard forms you need to memorize. Now let's come to actual interesting integration, that is definite integration. So we have to cover definite integration, Leibniz rule, and then length, surface area, and volume of a curve. So let's go through these quickly. So if I have this indefinite integral, say this is some capital Fx plus c, then I define this quantity to be capital Fb minus capital Fa. And magically, this doesn't care about this arbitrary constant that we kept on talking about repeatedly. Okay. But before I proceed further with this, how do you write an integration as a sum? So note that integral from a to b of fx dx is this limit. So if you see some ugly limit in a question, it might be some simple integration as well. Okay, where h is equal to b minus a for n. But given a limit, how do you go about converting this into the integral? So obviously, you could memorize what fits where, but let me give you some steps. So converting the above limit into a definite integral. So step 1, express or write it as a summation over 1 over n f of r over n. Okay. Then you let n go to infinity. So you have limit n tends to infinity, summation over 1 over n f r over n. So the summation is of course over r. Now you do some replacement. So you replace r over n by x 1 over n by dx, and this entire symbol by the integration symbol. Now you need the limits of the integral as well. So the lower and upper limits of integration are the limiting values of r by n for the first and last term of r respectively. The smallest and the largest, that's a better way to phrase it, I guess. So for the smallest and largest value r respectively. Okay. Now some properties of the definite integral. So we are going to go a bit over time today, maybe 10-15 minutes, so I can cover everything in ample detail. So if you flip the limits, you flip the sign. That's number one. And you can split it if it suits you over any C. So this can be any C such that the integration is still meaningful. It doesn't need to be between A and B. It can be anything as long as the integration doesn't stop making sense. Of course, you don't really know how to decide when an integration stops making sense. You can write it in this way. Might be helpful. You have an integration from 0 to some A. Then you can actually write it this way. Okay. If you have an integration from minus A to A, and that is just integration from 0 to A, fx plus of minus x, x. Right. And if need be, you can also convert any integration into an integration from 0 to 1. So okay. Now, if f happens to be a periodic function, so if fx is periodic with some period t, then I have some more additional properties. Number 7, a plus some multiple of the product of the period. Zero to a, this is a to a, so this should be 0 to t map. N is an integer. Similarly, from mt to nt would be n minus m, 0 to t, fix dx. Here also m and n are both integers. And finally, if you have a plus nt to b plus nt, then this is of course just a to b. And here as well, n is an integer. Okay. So now you have the Leibniz rule. Change colors again. And this is a very important topic for the result to know. If gt is continuous on a comma b, and f1x and f2x are differentiable functions. With values who lie in this interval, then the derivative of this integral is equal to g at the upper limit times derivative of the upper limit minus g at the lower limit times derivative of the lower limit. Fine. Have all of you seen this before? So a special particular case, in particular, d over dx 0 to x gt dt is just g of x. Okay, this is Leibniz rule. Now we have some inequalities involving the definite integral. Okay, so I have this, so mod of the integration is always less than or equal to the integration of the mod. Equality holds when fx doesn't change sign. That is when putting the mod inside or outside is meaningless. It's equivalent in the closed interval. Okay, that's one. Then you have if fx is always greater than equal to gx for all x belonging to some a comma b, then you can take the definite integral on this closed interval and the inequality is preserved. This is a very important factor, that taking the definite integral preserves such inequalities. Okay. Number 3. For a given fx continuous on AB, closed AB, if there exists f1x and f2x also continuous in AB, such that for all x belonging to AB, we have this inequality holds. So this is somewhat, so maybe not really. So if you have these 3 inequalities, then of course, as a immediate corollary of the previous fact, you can just integrate all of these, right? So you can do this way as well. Doesn't matter if you have more than one inequality going on at the same time, it still works. Okay. Now, of course, this implies that if this and this are equal, then the middle one has to be equal to that as well. So that's where a similarity to uh, that thing, sandwich theorem, can be seen, right? Okay. Now you have. Do you have now? Oh yeah, you have this as well. So whatever number this was, so let me just write 10 because I know it's not more than 10. If m and m are minima and maxima, of fx respectively in a comma b, then minima times the length of the interval is less than equal to the integration over that interval. It's less than equal to maxima times length of the interval. And to visualize this, you can think of rectangles. Okay. Now, of course, you know that integration gives the area, so I'm not going to mention that. But there are three important formula. So there are four results left that I want to talk about now. One of them I should have discussed previously, but I seem to have forgotten about it. So let's start with that one. So result one, let's call them A, B, C, D. A, the intermediate value property. So what does this say? This says that if fx is continuous on a comma b, then there exists some x naught belonging to a comma b such that f of x naught is equal to some y, and this works for all y belonging to this interval. So here I should mention that, or no, it's just I forgot the counting, so I just put 10 without any reason. That's what that was. I forgot which the previous inequality was numbers. Don't worry about it. So essentially, if I know that a continuous function takes two values, then I can be sure that it takes every value between those. That's all that this is in a fancy schmancy way. Okay. And now these are some integration results that you should memorize. And CMI asks these a lot. ISI mentions these on the back of tomato, but I don't think I have ever seen a problem from these. So let fx be continuous on a comma b and differentiable on the open interval comma b. Then you have, okay, and let f dash x, so you force one more condition, be continuous. You force this to make sure that you can integrate f dash x. Once again, you cannot always integrate the derivative. So there is some idea that people think that the integration is somehow the antiderivative and integration of the derivative is the original function. That doesn't always work. If you want to look up a counter example, Google Volterra's function. But you won't really understand anything at the moment. but this doesn't always work, so don't do that. If you have a continuous derivative, then it works, but in general, no. Then the length of fx, so the length of the curve between a and b is given by this formula. So some L is equal to the integration from a to b, the square root of 1 plus f dash x squared dx. How many of you have not seen this before? Okay, so these are something you need to know for CMI. CMI definitely, ISI it's good to know, but CMI asks like direct problems. So just they give you the function and they ask you for the length or two more formulas that I'm going to discuss. So make sure you download the boards later and write this down. Or if you want, you can write this right now and let me know when you're done. So just write the formula and you can make up the rest. Okay. So now you want the surface area. Oh, I need to draw a figure now. It's clear what I'm talking about. Or rather, let me write my conditions first. So let y is equal to fx be a continuously differentiable function. So continuously differentiable just means that it is differentiable and the derivative is continuous. An even more fancy way of saying this would be that, sorry. Yeah, so an even more fancy way of saying this is f is of class C2, which is something you don't understand, that you don't need to. So continuously differentiable just means that it is differentiable and that the derivative itself is also a continuous function. Continuous function on a comma b and a b respectively. So differentiable, continuous on a comma b, and then differentiable and the derivative is continuous on a comma. Okay. So now I want to do something to this. What do I want to do? I want to revolve it. So if we revolve fx around the x-axis, we obtain a solid. As shown. What solid do we obtain? We obtain something like this. I have this, suppose this is my x-axis. This is my A, this is my B. Say it's this value at A, some value like this at A, and then it's joined like this. Okay. So you just revolve it. So you go all the way around over here. And they should be symmetric. So something like this, right? Do you see the solid? Is there anyone who doesn't still get what the solid I'm talking about is? So this is all the way around. So this line makes a 360 degree, or rather revolves around the x-axis and sweeps a solid. Suppose the line is drenched in ink, so the curve is drenched in ink, and then if you revolve it around some sort of 3D paper, this is what you get out. Or however you want to think about it, okay? So then for this solid, you have two things. The surface area. So this doesn't include these circles. So the top and the bottom discs are not included in this. The surface area is equal to 2 pi times the integration from a to b fx square root 1 plus f dash x squared dx. And the volume is pi times integration from a to b of just fx squared. And that is all you need to know about calculus. Let me download the boards before I forget. And are there any questions? None? Okay, then that's all for today. Goodbye. Do you have a question? Does someone have a question? People are typing. Thanks. Thank you. Okay. Bye bye.